Okay, our topic this time is sigma notation. It has defined sigma notation as a way of writing a sum of many terms in a concise form. This Greek letter called summation sign, I as the index of summation, 1 as the lower limit of summation, n as the upper limit of summation, and x sub I as the typical element of the summation. For example, summation of 3i as I, this is read as the sum of 3i as I goes from 1 to 5. So substitute I starting from 1 to up to 5, multiply and combine, so the summation is 45. Next, the summation of key plus 8 as key starts from 2 to 7, substitute key starting from 2, 3, 4 up to 7, add, combine, so the summation is 75. Next, the summation of 2 to the power of I plus 1 as I starts from 0 to 5, substitute I starting from 0, 1 to up to 5, simplify and raise to powers, so the summation is to 126. Next, summation of g over 4 starting from 1 to n, substitute g starting from 1 to up to n. Okay. Next, summation of k minus 2 over k plus 2 as k starts from 0 to 6, substitute k starting from 0, 1 to up to 6, combine and simplify, reduce to lowest term, cancel out opposite signs, rename the fraction into similar fraction, combine, and the result is 9 over 70. Okay, write the following series using sigma notation. Number 1, as we examine the terms of the series, it forms an arithmetic sequence with the first term 5. So this formula is the nth term of an arithmetic sequence. E sub 1 is the first term, which is 5 in our series. D, the common difference is 2. Distribute 2 and simplify, combine similar terms. We can write 3 as 2 plus 1 so that we can factor out 2 outside. So 2 times n plus 1, and let k equals n plus 1 so that the simplified form is 2k plus 1. We will substitute k equal to 2 so that we can determine the first term of the series, which is 5. So our summation is summation of 2k plus 1 starting from 2 to 8. Okay. Next example, 1/4 plus 1/8 plus 1 over 16. As we examine the denominators of the fraction, 4 can be written as 2 to the second power, 8, 2 to the third, 16 is 2 to the fourth, 32 is 2 to the fifth. So our summation is 1 over 2 to the power of k, or it is equal to 2 to the power of negative k starting from k equal to 2 up to infinity. Next, a sub 2, a sub plus a sub 4. We can rewrite the subscript as 2 times 1, 2 times 2, up to 2, a sub 2 times 10. Our summation symbol is summation of 2i, or a sub 2i as I starts from 2 to 10. Okay. Next example, 4/3 plus 4 over 9 over 4. As we examine the numerator, they are perfect squares. So we can write the numerator as 2 square, 9 is 3 square, 16 is 4 square. And as we compare the numerator and denominator, the base of the numerator is 1 less than the denominator. So if we let k as the denominator, the numerator, the base of the numerator becomes k minus 1. So our summation symbol is summation of quantity k minus 1 square all over k as k starts from 3 to 8. Okay, next, let us proceed to properties of sigma notation. We have the property and example. First property is summation of C starting from 1 to n is equal to C times n. For example, summation of 5 starting from k equals 1 to 8. So that is the same as adding 8 terms of 5, or it is equal to 5 times 8. 5 times 8 is 40. Second property, summation of C A sub k as k starts from 1 to n. We may move C before the summation symbol. For example, summation of 2k square as k starts from 1 to 3. Move or write 2 before the summation symbol. And substitute k starting from 1 to 3. Simplify and multiply. So the summation is 28. Third property of sigma notation, the summation of quantity E sub I plus or minus B sub I as I starts from 1 to n is equal to, we can distribute the summation symbol to E sub I and B sub I. For example, summation of I square minus I as I starts from 1 to 3, that is equal to I substitute I starting from 1, then 2, then 3. So 1 square minus 1 is 0, 2 square minus 2 is 4 minus 2, 9 minus 3. Simplify, 2 plus 6 is 8. Or the distributed form of summation of I square as I starts from 1 to 3, so 1 square, so 1, 2, and 3 is squared, minus I starts from 1 plus 2 plus 3. Simplify and combine, so that is equal to 8. So they are equal. Okay, so the two summation property are the same. Okay, we have another property called telescoping sum property. The summation of quantity f of I plus 1 minus f of I as I starts from m to n is equal to f of n plus 1 minus m. Let us prove this property. So if we substitute I starting from m, then that is equal to f of m plus 1 minus f of m. The next term is m increased by 1. So that is m, or rather f of m plus 2 minus f of m plus 1. Plus the next term, again m is increased by 1. So we have f of m plus 3 minus f of m plus 2. Plus up to the last term, f of n plus 1 minus f of n. Okay. There are terms that can be cancelled because they are opposite in sign. F of m plus 1 is cancelled. Another term to be cancelled, f of m plus 2. Take note that the next term, the second term inside the quantity is the first, is the one that is being cancelled. So we can cancel out f of m plus 3 because the next term has negative m, or rather f of m plus 3. So negative f of n is cancelled because there is a term before it which is positive f of n. So what is left is f of n plus 1 and negative f of m. So we have proved the property. Okay, evaluate the following sum. This summation is something telescoping sum. So summation of quantity 1 over square root of key minus 1 over square root of key plus 1. Substitute key starting from 1. So 1 over square root of 1 minus 1 over 1 plus 1 is square 2 over square root of 2. The next term, 1 over square root of 2 minus 1 over square root of 3. So with the next term plus another term, okay, and last term in the series is we substitute key equals 24. Okay, there are opposite signs, terms which have opposite signs. Negative 1 over square root of 2 is cancelled with the positive 1. Negative 1 over square root of 3 cancelled. Negative 1 over square root of 4 and positive cancelled. Negative 1 over square root of 5 cancelled out. This negative 1 over square root of 6 has its opposite sign in the next term. And this 1 over square root of 24 has its opposite sign before this term. So what is left is 1 over square root of 1 and negative 1 over square root of 25. So simplify. It is equal to 1 minus 1 over 5. Square root of 25 is 5. Rename 1 as 5 over 5 and subtract. So the summation is 4 over 5. Okay, next properties. Sum of the powers of the integers. We have the sigma notation in closed form and the expanded form. Example, summation of 1 as key starts from 1 to n, it is equal to n. Or we add 1 plus 1 n times because there are n terms. So summation of key as key starts from 1 to n. Another property, summation of key as key starts from 1 to n, it is equal to n times quantity n plus 1 over 2. For example, 1 plus 1 plus 3 up to n, that is, we can make use of the formula n times n plus 1 over 2. The third property, summation of key square as key starts from 1 to n, it is equal to n times quantity n plus 1 times quantity 2n plus 1 all over 6. For example, starting a value of key with 1 square plus 2 square up to n square. Simplify. Okay. Next, another property, summation of key cube as key starts from 1 to n, it is equal to n square times quantity n plus 1 square all over 4. For example, if key starts from 1 to up to n. Okay. Let us have some examples using the properties of sigma notation. Prove that summation of 3i square minus I minus 2 as I starts from 1 to n is equal to n times quantity n plus 2 times n minus 1. Okay. Distribute the summation symbol to its term, making use of the property that we have discussed a while ago, these three properties. So substitute the summation symbol with 3 move before the sigma notation. So 3 times summation of I square as I starts from 1 to n minus summation of I as I starts from 1 to n minus summation of 2 as I start from 1 to n. Okay, using the properties, Summation of I square, we have the formula n times n plus 1 times 2n plus 1 all over 6 minus n times n plus 1 all over 2 minus 2 times n. So following these properties that we have, we come up with this after using properties. Okay, 3 and 6 can be reduced. Okay, in each of the terms, common factor is n over 2. We can rewrite the whole expression with n over 2 outside the parentheses. Inside the quantity, simplified, the distributed and simplified combine similar terms. Then in its term, 2 is common. We can move 2 outside. Then cancel out 2. Then the quantity is written in factored form. So n square plus n minus 2 is in factored form. N plus 2 and n minus 1. So we have proven the value of the summation. Okay, next example. Find the sum of summation of 3k minus 2 as k starts from 15 to 100. We can make use of distributive property. Distribute the summation symbol with 3k and negative 2. 3 is moved before the summation symbol, and making use of the property that you have learned. So this becomes, take note that our property key starts from 1 in our problem, key starts from 15. So change key equal to 15 to key equals 1 so that we can use the property. So we may rewrite as 3 times the quantity summation of key as key starts from 1 to 100 minus summation of key where key starts from 1 to 14. So summation of key starting from 1 to 14 is removed from summation of key starting from 1 to 100 minus summation of 2 starting from 1 to 100 minus summation of 2 starting from k equal to 1 to 14, and use the property and simplify further, and subtract. So the answer is 14,663. Okay, write its series using sigma notation. Okay, we have our series, all are negative. So we can remove negative outside the parenthesis, and examining its term in the series, we can factor out 8 as 4 times 2, 18 as 9 times 2, 32 as 16 times 2, up to 200, which is 100 times 2. The 4, 9, 16 up to 100 can be written in where these numbers are perfect square. So the base are increasing 2, 3, 4 up to 10. In other words, our expression for the series is negative n square times 2, or our summation symbol is summation of negative 2n square as n starts from 2 to 10. Next problem. Square root of 3 is common in its term, so we can remove square root of 3 outside the parenthesis, and inside the parenthesis 3 plus 5 plus 7 up to 39. It forms an arithmetic sequence with the first term 3, common difference is 2. So simplify, combine, we have 2n plus 1. So our expression inside the parenthesis is 2n plus 1. Now, in our summation symbol, what is our index of summation? Our lower limit and upper limit. We substitute e sub n with 39 and solve for n. Our value of n is 19. So our summation symbol has index n equal to 1 up to 19. Okay. Next problem. We can change 3 as 3 over 1. The numerators form a geometric sequence. So we will make use of the denominator also. The denominator forms a geometric sequence with a common ratio of 2. The first term is 1. So using the geometric sequence formula, the first term e sub 1 is 1, the common ratio is 2 to the power of n minus 1 in simplified form. The numerator forms a geometric sequence with the common ratio 3. The first term is 3. Substitute in the formula and simplify. Okay, so that is 3 times 3 to the power of n minus 1. Okay, we can let key equal to n minus 1 so that it becomes in simplified form. 3 times 3 to the key over 2 to the key. The numerator can be simplified further as 3 to the key plus 1. So our summation notation is summation of 3 to the power of key plus 1 all over 2 to the key, as key starts from 0 to 4. Use the properties of sigma notation to evaluate the following summations. Summation of quantity k minus 1 square. First step is raised to powers. K minus 1 square becomes k square minus 2 k plus 1. Next step, distribute the summation symbols. Summation of k square, k starts from 1 to 32 minus 2 times summation of k starting from 1 to 32 plus summation of 1 starting from 1 to 32. Using the properties of sigma notation that we learned, this becomes n times n plus 1 times 2n plus 1 over 6. That is the property. Minus 2 times n plus 1 over 2 plus 1 times 32 using the summation property. Simplify. Substitute n equal to 32 and simplify again further until we eliminate the fraction. 32 times 33 plus 32, and the result is 10,416. Next, evaluate the summation of 1 over square root of I plus 1 plus square root of I as I start from 1 to 99. Okay. Now, as we examine, the fraction is complicated in its we can rationalize the fraction by multiplying both numerator and denominator by the conjugate of the denominator, which is square root of I plus 1 minus square root of I. So multiplying the numerators and denominators, the result is square root of I plus 1 minus square root of I all over I plus 1 minus I. Then negative opposite signs are cancelled. So we are left with the numerator all over 1, or it is equal to square root of I plus 1 minus I. So our new summation expression becomes summation of quantity square root of I plus 1 minus square root of I as I start from 1 to 99. Okay, substituting I starting from 1, so I plus 1 becomes 1 plus 1, or square root of 2 minus square root of 1. And next succeeding term, square root of 2 minus square root of 3 minus square root of 2 plus square root of 4 minus square root of 3. And the last term is the square root of 99 plus 1 is 100 minus square root of 99. There are terms which are opposite in sign, like square root of 2 and its opposite sign, square root of positive square root of 3 and negative square root of 3, square root of 4 and negative square root of 4. Take note that the second term in its quantity, in its parenthesis, is the one that is being cancelled. So negative square root of 99 is cancelled. So what is left is square root of 100 and negative square root of 1. So that is equal to square root of 100 minus square root of 1. Square root of 100 is 10, square root of 1 is 1. So 10 minus 1 equals 9. So that is the value of the summation. So thank you. That's enough.